So just to remind you what our problem was, we had an aircraft of a certain capacity and customers, passengers of two types were booking tickets for our flight. We knew the prices for each class, and we knew the demand forecast, and we wanted to protect the seats, to reserve the seats for the business customers, which pay more but reserve tickets later. So we want to protect certain number of seats for the business passengers, so that when they come, they have enough seats and can pay the larger price for those seats. So here are some of the specific values on specific letters that describe different parameters that we have in the input in the problem. So we assume that the capacity of the plane is 100, and as we briefly discussed, it really doesn't matter. What we are looking at is the percentage of the seats that we have to reserve for the business passengers. So this should scale to arbitrary capacity of an aircraft. In fact, we will look at a problem where the capacity is 90, just for an example. But anyway, for our basic problem, we will be looking at an aircraft of capacity 100. So we know the two prices. Capital R is the price that a business passenger pays, and small r is the price that a leisure passenger pays. And the demand forecast is reasonably simple. For the leisure, we assume that they in principle can fill all the aircraft. Every seat, if you want, you can sell you can sell all the seats to the leisure passengers. So the demand in the sense is deterministic and, well, basically unbounded, infinite. But we only have 100 seats on the plane, so okay, so leisure you can get most 100 passengers. Now for the business passengers, things are more interesting, and this is exactly where the probability comes into play. The number of business passengers is a random variable. We don't know in advance how many business passengers will come. Well, if we knew, we would have reserved exactly that number of seats. So what we know is the distribution of this random variable. And essentially this probability review that we did in the last lecture was about, well, what does it mean that we know the distribution of the number of business passengers or of any random variable? What are the different functions associated with the distributions, and so on. So deterministic forecast for the leisure and this random or probabilistic forecast for the business. And we want to find the number of seats. Well, here I'm saying to protect for each class, but since we only have two classes, so we're really protecting only for the business passengers, and the leisure fill the remaining part of the plane. So yeah, even in a Mossack statement, we are given two revenues per seat. One is larger than another. The number of business passengers is the random variable. The cumulative distribution function of this random variable will be denoted by f. This function specifies what is the probability that y, the number of business passengers, is smaller than a certain number, the argument of the function. And, well, we have this notation x. This is the unknown. This is the number of seats that we will want to protect for the, or reserve for the business customers, and the leisure will fill the rest. And our goal, the objective, is to maximize the expected revenue. Why expected? Because we don't know the revenue with certainty. The number of business passengers is a random variable, and hence our revenue is a random variable. We don't know what it will be, but we want to reserve the number of seats such that the expected revenue is maximized. And this expected revenue is the expectation of the random variable. Again, we looked at what the expectation of random variable is as a review last time. So that's the problem statement. I hope you have refreshed your memory from the last time. If not, well, that's what it is. So let's see. What will be the revenue from leisure passengers if we reserve X seats for the business passengers? Well, for every seat, we get the revenue of small r, and while overall capacity is 100, X is reserved for the business. So how many will be sold to the leisure? 100 minus X. Each goes at the price of small r. So what is the total revenue from the leisure? Well, simple mathematics. 100 minus X seats. Well, not in really 100 or 100 minus X times r. So X seats go to the business. So leisure have 100 minus X, and each of them goes for r, small r. So that's the revenue from the leisure. Okay, nothing complicated here. With the business, things are more interesting. How many business tickets will we sell? So again, we have X seats reserved for the business, and the number of business passengers that come is Y. So how many tickets will we sell? Let me draw a very schematic example. So here is our aircraft, and draw it more as a rectangle. So we have reserved X for the business, and the rest goes for the leisure. And now Y business passengers have come. That's a random variable. So how many seats will we sell? Well, let's see. If Y is smaller than X, maybe I should have removed, that was the wrong place to annotate. So if fewer business passengers have come than the number of seats that we have reserved, then how many business tickets will we sell? So I don't know, maybe we have reserved 100 for the business passengers, but only 20 have come. Yes, then in this case, we will only be able to sell Y seats, right? We have reserved, I don't know, 25, but only 15 have come. Well, we can only sell 15 tickets. So if fewer business passengers came than what we have anticipated and what we have reserved, well, then we sell as many tickets as there are business passengers that want to fly our aircraft. We over-reserved. Okay. If more business passengers have come than the number of seats that we have reserved, then how many tickets will we sell? Yes, in this case, we sell X. Again, maybe, you know, maybe 100 business passengers want to fly our aircraft, but we have reserved only 2 seats. Well, we would have to deny all the other business passengers and sell as many as we have reserved. Again, our model is that we have reserved and the certain number of tickets for the business passengers and sold all the other for the leisure passengers. Of course, in practice, yes, it happens that people are denied boarding, but I mean, in our model, we have, okay, we sold it to the leisure, so they should get their seats. So if more business passengers came than the number of seats, then we sell the number of seats. In short, if you want, we can say that we sell minimum between Y and X. But essentially, this is the only kind of small piece of logic behind the revenue management. Everything else will be pure kind of mathematics, arithmetic. So starting from now, we will go into a few formulas and we'll write out the expression for the expected revenue and then find the optimal seat reservation level. So we know this, and we know how many business passengers will come. So what will be our revenue from the business passengers? Well, let's calculate it. If no business passengers come, of course, we don't get any revenue from them. If one business passenger comes, we get, well, we sell one seat, we get revenue of capital R. If two business passengers come, we get revenue 2R, and so on and so forth, all the way up to X business passengers coming. So I'm looking at the chat. Are you only available to plan these kinds of stuff when you buy a plane? Depending on that. So that's a good question. I mean, how is it physically done? Yes, I mean, in general, you kind of decide in this when you're buying a plane, how many business and different classes of seats you will have. And we saw these pictures of Airbus 380. But in many cases, again, as we discussed, it's really not about the physical layout. This is just, yes, so as somebody answered, some airlines can change the business class sign in the cabin. They would just move exactly this business class sign or whatever, or the location of it. Yeah, so up to here is the business class. Everybody back is the economy class. So it's not that much about the physical things. It's more about the services that you get being in a higher class or something like that. And yes, I mean, if you pre-order the aircraft with a certain number of seats reserved for different classes, then also the distance between the seats is different, the seats themselves are different, and so on. But even if you just have an aircraft where all seats are the same, still, I mean, depending on the level of service and other things, you can really decide it on the per flight basis. So yeah, so here we're talking about what's the number of seats reserved for the business. Okay, so continuing with the calculations of the revenue from the business passengers, if fewer business passengers come than the number of seats that are reserved, if K business passengers come, we get K times R. We serve all the demand, we sell the ticket to every business customer. And if more, well, okay, if exactly X business passengers came, well, then we are happy, we sell exactly that number of tickets. If more business passengers come, we still sell only XR. We still sell only X tickets, and our revenue is only XR. So, well, we underestimated, we could have gotten more, there is some lost revenue, but we reserved X, Y came, Y is larger than X, we only get the revenue of XR. So these are the kind of different revenues that we get from the different number of business passengers. Now let's calculate the expected revenue from the business passengers. Again, just to remind you, in a nutshell, when you want to calculate the expected value over a certain random variable, you multiply all possible values for this random variable by the probability that this random variable will get this value. Or in terms of the functions, you are multiplying the values by the probability mass function. So we had examples, and here is one example. So we have probabilities of this random variable y getting certain values, and we are multiplying each of these revenues by the corresponding probabilities. So we are weighting these values by the probabilities. So we multiply this by this, plus this times this, plus this times this, and so on. So here is the formula for the expected revenue from the business passengers. It's 0 times the probability that 0 business passengers will come, R times the probability that 1 business passenger will come, and so on and so forth. In general, K times R times the probability that K business passengers will come if K is smaller than X. And if the number of business passengers is larger than X, then we're multiplying it by X times R, because we only sell X tickets, and each ticket goes for capital R. Okay, so here is the kind of more succinct formula for the revenue from the business passengers. Summation for all possible values of K, where K is the number of business passengers. The revenue times the probability. And here the same thing. The revenue times the probability. That's the expected value. And well, here is the formula for the total expected revenue if we reserve X seats. Okay, so X is our unknown. So we have reserved X seats, and we have certain revenue. So this is the revenue that we get from the leisure. And these two terms is the revenue that we get from the business. And in a couple of problems on homework 2 and also on the exam, you will have to calculate this for, well, certain flights. So you will be given the probabilities, the probability distribution for the number of business passengers. You will be given the number, well, the prices for the business and for the leisure seat. And you will have to calculate this formula for a particular instance of the problem. We will have example also in class and also in homework. Okay, but so this is just the general formula. We still have to understand what is the optimal X, what is the best seat reservation level that gives you the highest expected revenue. And this is what we will be doing for a couple of slides. Right now, again, we have the formula, so everything starting from here is, well, purely technical things, but we will be using certain notions that you might have studied in calculus or analysis or whatever that mathematical course was that you took. General question. So we have this formula, and it's a function of X. So X is a variable. Depending on what X is, the expected revenue can have different values. How do we maximize a function of X? So we have some function of X. How do we find the maximum of this function? I'll just draw an example. Maybe you have these things. This is your X. And, well, you have some function of X. How do you find the maximum? Or maybe a local maximum. Do you remember what you did in the, yeah, this is f of X, in your analysis course? So you might remember that something that you could do to maximize or minimize the function is to take its derivative. So you take the derivative of the function with respect to X and set the derivative to 0. So you differentiate with respect to X and find the point where the derivative is 0. So we could, or we actually want to differentiate this expected revenue with respect to X in order to find the best X, the X that maximizes the expected revenue. There is one problem, or at least one problem with differentiation, is that this term is not really differentiable with respect to X. It's not some kind of linear function or quadratic function or something else. You have the summation, and the X here is the limit of the summation. How to differentiate such a thing with respect to X? I mean, in principle, it's non-differentiable. And here we can use a little trick that you might have seen done in physics, if you had physics classes. If not, well, we'll look at the relation between the sum and the integral. So if this blue thing is your function f of X, then, well, the area under the blue curve is the integral of the function. Hopefully you remember this. Well, it's not really a definition, but one understanding of the integral. That integral is really this area under the function, this whole And what is the summation that I have here in the lower left corner? What is the summation in terms of this function? Well, when you do the summation, you assume that the function is constant and only changes at integers, 1, 2, 3, and so on. And so this gray here, which consists of several rectangles, each rectangle has width 1, and the height of the rectangle is the value of the function at 1, 2, 3, and other integers. So this gray area is exactly this sum. So again, the integral of the function is the area under the blue curve, and the sum is the total area of these gray rectangles. And well, they're kind of close to each other. They're not exactly the same because you have these little white spaces where you're undercounting, and you also have these little gray things that come out of the blue curve. But more or less, you can assume that these things are approximately equal. So you can approximate the summation with the integral. Okay. And now we can write the expected revenue and say that it's, well, approximately equal to this thing where we have replaced the summation with the integral. Okay. So now to put it back into the parlance of the probability theory that we were looking at, let's look again at certain functions that we discussed last time. The probability mass function is the probability that the random variable is equal to a certain number for each of the numbers. So this function tells you how much of the probability mass is concentrated on any number. And a related notion, the probability distribution function for a continuous variable, which again, well, in a sense, tells you how much mass is concentrated on every point. But now these points are not only the integers, but in principle, yeah, it's defined for any number. So these are similar functions. The probability mass function is for discrete random variables. Probability distribution function is for continuous random variables. So we can rewrite the expected revenue like this, like I have at the bottom. And here I replaced this probability, the probability that y is equal to k, with the probability distribution function of y. So again, we're saying that, well, this thing is well, equal to this. And so I'm replacing this with this because of this equality. Okay, so we have here at the bottom, we have the new formula for the expected revenue, a bit more of usage of the functions that we have defined in the previous lecture. Cumulative distribution function, I guess that's the main one. That's why usually if we speak about distribution function for a random variable, we really mean the cumulative distribution function. Probability that shows that the random variable is smaller than a certain number. And in particular, the probability distribution function is the derivative of the cumulative distribution function. Again, we had it in the last lecture, but you might have heard it. Otherwise, if not, that's what it is. Also, this probability that the random variable is larger than a certain value is really 1 minus its cumulative distribution function. Again, we mentioned that in the last lecture. So the formula for the expected revenue, we now rewrite it using only the distribution function, only the cumulative distribution function. So we're replacing the probability density function with the derivative of capital F of the cumulative distribution function. Well, here is y. And we are replacing this, the probability that y is larger than x, with this 1 minus the probability that y is smaller or equal to x. So essentially, all these manipulations with the formula, they were needed to have the formula depend only on one function, on this f, the cumulative distribution function, which we have for any random variable. So not to deal with this probability density function, not to deal with probabilities. Now we have the formula, which only depends on the cumulative distribution function. And this is something that we are given in the input. So we know the distribution of the number of business passengers. What does it mean that we know the distribution of a random variable? Well, we know its cumulative distribution function. So this f is given. Okay, so we have this formula, and now we can differentiate it with respect to x. So remember, we want to find the x which delivers the maximum to the expected revenue, and for that we will find the derivative, set the derivative to 0, and that will be our answer. Okay, so what is the derivative of this thing? So this is our function, and I'm using this subscript x to indicate the derivative. Well, there are various notations for the derivative. This is one possible. So the function consists from 3 terms, 1, 2, 3. And well, the derivative of the sum is the sum of the derivatives. And probably the easiest term to take the derivative is the last term, the revenue from the business. From the leisure passengers, but whatever. By now we have forgotten what these terms mean. We just playing with this formula. So yes, the derivative of this term, the derivative of this, it's a linear function of x, and the derivative of linear function is well, just the coefficient in front of x. So this is minus r. Again, if you really want to keep track of what these different terms mean and what these derivatives mean, well, you can still do it, at least with the leisure passengers. Essentially, what this is saying is that every time when we increase x by 1, we lose small r in the revenue from the leisure passengers, right? And if you give 1 seat to the business passengers, then you don't sell it to the leisure passengers, and hence you lose small r, and that makes sense. Your derivative with respect to x of this term, the revenue from leisure, is minus r. You increase x, you lose the revenue from the leisure passengers, and you lose it at the rate small r. Okay, so that was the simplest part. The other parts are not too complicated, so let's look at them. The derivative of this term. Okay, this term is the product of x, capital R, and this thing. Now, capital R is a constant, so we just take it out of the parentheses. So if you multiply a function by a constant, then its derivative is also multiplied by that constant. And now we have to take the derivative of this times this. And you may remember that the derivative of the product of 2 functions, u times v derivative, is equal to the derivative of one function times the other function plus the derivative of the other times the first one. Sorry for my scribbling and using the mouse. But anyway, that's just the formula for the derivative of the product of 2 functions. And well, here we have, yes, 2 functions, this and this. The derivative of x is 1, and we multiplying it by this function. Here it is. And then we take x, here it is, and multiply it by the derivative of this. And the derivative of this is just, well, here it is, minus times the derivative of f. Because we have minus here, we have minus here. So again, pretty standard things in calculus. Okay, and last but not least, we have this term. And here we take the derivative with respect to the upper limit of the integral. Okay, so we have integral of some function, f of x, well, let's say it's f of k, and the integral goes from 0 to x. So this the integral, okay, is the dummy variable, and we want to take the derivative of this thing with respect to x, where x is here. X is the upper limit of the integral. And I don't know if you learned that, but if not, it may make sense that the derivative of a function of the the derivative of the integral with respect to the upper limit is really the integrand, the function at x. So again, if you look at this interpretation of the integral as the area under the curve, so you have your function, and at any particular x, this integral going from 0 to x is the area under the function between 0 and x. And the derivative of the integral, the derivative of this area, shows you how fast the area changes as x increases. So if x increases, the area also increases, and the derivative is the rate at which the area increases, because the derivative of any function is the rate at which the function increases. In particular, the derivative of this integral is the rate at which the area increases. And it's kind of natural that the rate at which this area increases is equal to the value of this function at x. Right? So if the function is small, if f is small, then by increasing x, you only increase in the area by something small. If f of x is large, so here as you increase x, the area increases by something larger. So it increases by exactly the value of the function at x. So that was the intuitive explanation, but there is also a proof, and maybe you have studied that. So returning to our the derivative, so the derivative of this integral with respect to x, where x here is the upper limit of the integral, is the value of the integrand of the function that you're integrating at x. So here is what it is. So you replace this with x and this with x. Okay, so that's one time when something that you learned earlier in calculus and in probability comes into single place. So yes, that's how it goes. You learn some foundations, and now you're starting to apply them. So here you apply knowledge of calculus and knowledge of probability. And in particular here, we have differentiated the expected revenue with respect to x, with respect to the number of seats reserved for the business customers. Okay, we have the derivatives of all the three terms. So we put them together, this plus this plus this. And then after canceling certain terms, we obtain that the derivative of the expected revenue with respect to x is this thing. And we want to find the best x. We want to find the maximum of the function. So we set in the derivative to 0. And well, here is the answer. The optimal x is given by this formula. The cumulative distribution function of x should be equal to 1 minus the ratio of the revenues from the leisure and business. So before I let you ask your questions, if any few comments. One thing is that it makes sense that this solution, the optimal value of x, depends on the ratio of small r and capital R. Why? Because, well, think of the currency. You can think that these both small r and capital R are expressed in crowns or in euros or in dollars or in anything else. If you change the currency and scale both small r and capital R by the same scale factor, then that shouldn't change your decisions on the number of seats reserved for the business passengers. Right. I mean, what really matters is by how much more capital R is than small r. What is this factor? So yeah, it makes sense. And of course, small r is smaller than capital R. So from 1, you are subtracting something which is smaller than 1. So you do get a number between 0 and 1. And you remember that the cumulative distribution function is a function that starts from 0 at minus infinity and then increases to 1 at the plus infinity. But yeah, it goes between 0 and 1. So this is a well-defined level of the cumulative distribution function. You can determine what is the optimal seat reservation level. So these are just some kind of, qualitative things. Now, one thing which is still missing here, really from the quantitative analysis, is that, okay, well, we set the derivative to 0 and found the value of x where your function has a derivative equal to 0. I will again just draw this picture of a function of x. And you know that derivative at any point is the tangent, well, is the slope of the tangent. In particular, in the maximum, I wasn't very successful with drawing through the maximum, but I wanted to say that if you draw the tangent at the maximum, then the slope of the tangent will be 0. Well, that's good because that's what you're looking for. But also the slope can be equal to 0 at minimum. And well, we have set the derivative to 0 and determined a certain x. But how do we know? Are we at the maximum or at the minimum? Maybe this is the worst x. So do you remember from calculus, how do you distinguish between maximum and minimum if you have the derivative set to 0? So if not, I'll remind you. You take the second derivative and you look at what it is, or you look at the sign of the second derivative. So in our case, if we take the second derivative of x, which is just the derivative of this thing over x, and of course this term goes away, minus r, and then if you take the derivative of this term, then this is what you will get. And so the second derivative of the expected revenue with respect to x is minus r times the derivative of f, the derivative of capital F. And this derivative is what? So you know that the cumulative distribution function is never decreasing. It's increasing from 0 to 1. So you know that the derivative of the cumulative distribution function is positive because the function is increasing, and hence this whole thing is negative because you have minus here. And this is positive and this is positive. So the second derivative of the expected revenue is smaller than 0. And so wherever the first derivative is equal to 0, you actually do have the maximum. It's not the minimum. If the second derivative were larger than 0, then you would have been in the minimum. But here you're really in the maximum. Okay, so that completes the derivation of the optimal seat reservation level. So we still have 5 minutes in this part of the lecture. I'll just flip through a few slides and then we'll continue. So yes, here is the summary. We are given the revenues for the business and the leisure. We know the distribution of the number of the business passengers. And here is the solution. Here is how you find the optimal number of seats to reserve for the business passengers. You look at this thing, at the cumulative distribution function, and you check where it crosses this level, where the graph of this function crosses this level. So this is that, and the graph is increasing, and at a certain point it crosses this level. That's where you have the equality that f of x is equal to this. and this is your optimal X. This is how you determine the optimal number of seats to reserve. Okay. Yeah, I guess I still can speak about this even in this hour. Again, I just want to stress that the only thing that where we really kind of had to use our brains and think about the logic and about the process is understanding this saturation of the number of tickets that we can sell. So again, if I draw the graph, if you know, this is the number of seats that you get, then that you reserve, then your revenue grows and grows and grows. But at certain point, you cap yourself with the number of seats that you have reserved. And even if you have more business passengers coming, you still have the same revenue. I think I'm wrong. This is not X. Sorry, wasn't able to erase it. So on the contrary, this should be, trying to get back to the pen. So this is X, and this is the number of business passengers. So as the number of business passenger grows, and this graph shows your, well, your revenue from the business passengers. I'm going to draw what it is. So the more business passengers you have, the higher revenue you get. But at a certain point, you are saturated, and your revenue is really the minimum of X and Y. And of course, this saturation phenomena is not doesn't only show up in this particular problem with the seat reservation. You can see it in many other places. Too much product and your revenue grows, but then at a certain point you have overproduced. There are lots and lots of capacity limits. I also understand that we have a steep learning curve, and if I continue talking for longer, I don't think you will get much more knowledge from this lecture. You will probably be saturated. So let me stop here, even though there is 1 minute before 2, and let's restart at 2:15. So yes, we were talking about importance of the cumulative distribution function. And one question is, what distribution functions could you see in reality, in particular for the number of the business customers? And one realistic function is the function for the Poisson random variable. The Poisson processes are omnipresent. In particular, business passengers booking or other passengers booking, many of them, they follow the Poisson process. So Poisson process is something, well, it's relevant when you have, you know, some big bulk of things like people or stars or, you know, something else. And then you have these people or stars or things fall out from this bulk every so often. So there are lots and lots of people, and every so often, some of these people become business passengers on your flight. And the important thing is that the number of passengers on your flight is small in comparison to the overall bulk of people. If that's true, then Poisson process is relevant because it has so-called memoryless property. One classical example for Poisson process, which they use in stochastic processes, is a small cafeteria in a big university. So you have lots and lots of students, and you don't have, a central dining hall where you know that all students will come. I don't know, half students will come, but it's a small cafeteria. You don't know which students will come, which students will not come. You can model the customer's arrival as a Poisson process. Very common model. Also, I was mentioning stars because there is this famous problem about stars falling from the sky. It goes like this: if you sit and look at the sky for 10 minutes, the probability of seeing a fallen star is 10%. What is the probability of seeing a falling star if you look at the sky for 20 minutes? Of course, the kind of the straw man is that you could be tempted to say, well, I look for twice the time, so my probability doubles. Now my probability of seeing a fallen star is 20% within 20 minutes. Well, of course, then there is an obvious question. What if you look for 100 minutes? Is your probability to see 100%? If you look for 2 hours, is your probability to see a fallen star 120%? No, I mean, the way to answer this question is to say, well, the falling stars, stars falling forms a Poisson process, and you can get its intensity from what's given in the problem, and then answer all the questions about probabilities of seeing stars within different intervals. I mean, I know this problem. It was from one of the Wall Street interviews I took when I was a graduate student. So anyway, suppose some process, yes, very common model for customers arrival, saying that the number of customers is a Poisson random variable. And one interesting thing about the Poisson random variable is that it has only one parameter. You know, like if you think about the uniform random variable, it has two parameters, uniform between 0 and 1, or between 1 and 2, or something else. You need two parameters. Your normal distribution, you know, the bell-shaped, you need to know the average and you need to know the sigma. Two parameters. For Poisson, there is only one parameter, and it's called the intensity of the Poisson process. And here is the probability mass function for the Poisson random variable. And it's somewhat complicated, but still it's a function that gives you the probability of this random variable to be equal to k for every number k. And as you can see, it only depends on one parameter. And in particular, this parameter is really easy to estimate. So the expected value of the Poisson random variable and its variance both are equal to lambda. And yes, here is a snapshot of something that I had from Mikhail. Quite a few random variables that you looked at. Here is the Poisson. Tells you, yes, how many, the constant intensity in a certain interval. Yeah, there is another thing, right? So the accidents on the road, that's true. They also follow Poisson process. A lot of processes are actually Poisson processes. And yeah, so here's an example of a Poisson random variable with parameter lambda. Well, if you have a Poisson random variable with parameter 20, meaning that, you know, maybe on average you have 20 business customers on your flight. If you know that, you know anything you want. You know the probability that there will be 2 customers. All you need is to substitute 2 in place of k in the formula for the probability, and so on. Probability of 5 customers, the expectations, and many, many other things, and the variance also. So here's a couple of again pictures from the book. Yeah, the book is not mandatory, but still, if you're reading that, reading the book, you can see that. Yeah, it also said that assume that the arrival of the demand here is the passenger of a certain type distributed according to the Poisson distribution. It makes sense. The book then goes into how you do the seat reservation. It just tells you how many seats to reserve. I'm not going to go into the details. If you want to learn that and you're following the book, then ask me. I think I once understood how it's done. So again, so they have different classes, and they have the expected demand per class, and essentially this gives you the full distribution for the number of customers. So since they assume that the customers arrive according to the Poisson process, the number of customers is a Poisson random variable. So knowing the expected demand, knowing the expectation suffices in order to know the full probability distribution. And they also have these average fares, which we had capital R and small r for our 2 classes. We only look at 2 classes. And then there are lots of things. So these calculations you don't have to look at. Few other resources where similar things show up. One is this Wikipedia page, which, well, something called Littlewood rule. I'm not going to go into too many details on that, but basically just highlight that you have these R1 and R2, which are our capital one and capital R and small r. One is larger, one is smaller. And then if you look at this green box, which tells you the optimal level of seat reservation, yeah, they do look at the seat inventory problem. And this is exactly the same thing that we had. The F, the probability distribution function of the optimal seat reservation level should be equal to 1 minus the ratio of the prices of the revenues. So this is exactly what we have. They just don't derive it, but that's one resource that you may look at. So the revenue management lecture, so what I want to do now is to go through MIT set of slides. Again, just for you to see what things are the same and what things are different in their lectures. One thing which is, well, very similar, actually is the same, is that they do stress that yield, looking at the yield, is probably not the right thing. What we really want is the revenue maximization. So there will be a slide on that. This EPOD system, we don't study that. What we really look at is the single fare class seat allocation problems, single leg fare class allocation problem. So this is exactly what we looked at: one leg, one flight, seat allocation problem. And yes, we were looking at this nested booking, meaning that we look at the highest class versus all the other classes, and not trying to do the the several classes at once, as for instance the book does. Deterministic versus probabilistic, yes, that's exactly what we had. Deterministic for the leisure, probabilistic for the business. Yes, and we're not going to do the example of calculations. We'll just see how they are similar to what we did. So we did talk about this, well, differential pricing, as usual, fancy words for simple things. At MIT, essentially saying that, well, different products, different seats are offered at different prices, even if you travel on the same, well, actually even on the same flight, not only on the same origin destination market. Right, I think this is important to understand the difference of yield and revenue. So you might have seen yield in TNFL 01. If not, no big deal. I'm not teaching the yield. You can see what yield is. But the important thing is that, well, here I said revenue maximization is the proper goal. So you really need to do revenue management instead of yield management. And in a few texts, you can see that, well, we should get the higher yield. Well, you're really looking for the higher revenue management. So too much emphasis on yield, revenue per whatever the mile flown, may not be the right thing to look at. I'm not going into detail why it is so. Okay, so here is just an example. I don't think there is anything very interesting here. Overbooking. So we didn't look at that yet, but I do have it at the end of the demand modeling lecture, how to capture the no-show effects. Of course, this fare class mix is, yes, it is exactly what we looked at. Determine the revenue maximizing, that's what we did. Mix of seats, that's what we did. Available for each booking fare. We looked on that too. So this, yeah, the important thing, which I might have mentioned, is that origin destination, like single flight optimization versus the network optimization, that's something that we unfortunately don't look at. We look at a single flight, even though people buy itineraries, and itineraries may have several flights, and then there are all these questions: do you keep the same level of service on all the flights, or only on some of the flights in the itinerary? We ignored that. We didn't look at that. Yes, so revenue management is a complex problem. I guess we don't have to look at specific numbers. So we know what revenue management systems do, and we will eventually get to the like a block scheme of what a revenue management system does. But yes, you look at historical data and do the forecast, calculates the limits. That's exactly what we do. Overbooking, maybe we will well, we'll have it in the end of demand modeling lecture and so on. Then yes, we do it in one shot, but in principle, you can review your recommendations and change things if you know that certain events happen. I don't know, maybe there is some business meeting, so you may want to reserve more on your aircraft, more business seats. Of course, that's someone asked in the previous lecture. Yeah, if you really pre-order in the aircraft with a certain amount of business seats, then there's not much you can do. Well, I mean, you can still, people do get pushed, or at least there are some class upgrades that you sometimes can get. These are exactly the things that happen if the airline overestimated or underestimated the number of business customers. But yeah, you can do the reviews and change things if necessary. So looking at this picture, we will look at it a couple of times during the course. Few modules in the revenue management system. So as the output, you can see we want the recommended booking limits. And this is more or less what we studied. So we looked at this optimization model. What is the optimal number of seats? So this is the path that we took. So the revenue data, well, we didn't really look at it much, but all we know is this capital R and small r. So that's the input to our optimization model. The other input is the forecasting model, which we didn't look at in details. That's in the demand modeling lecture. But from here, we really get in this Y, the probability distribution for the number of business passengers. From the pricing data, we get the prices. From here, we get the forecasting model. So we more or less understand, or at least we covered this part of the revenue management system, these modules. Overbooking we will look at later. So forecasting model, historical and actual bookings, yes, and also no-show data. So that's for later. So now we have followed this path. Okay. Next, yeah. So dynamic revision and intervention, we don't do that, but yes, I already said, yeah, there are some unexplained surges in demand and human intervention may be needed. Yes, so a lot of airlines do the revenue management. I guess we understand that, but still there are quite a few that don't use any computerized revenue management system. They lose. Yes, we don't do the ePods, so I'm not gonna stop here. So this is the thing that we did, and we'll stop on it more to see what's different between us and MIT. So the single leg seat allocation problem, exactly what we looked at. So yes, you know the full capacity. You know there are several classes. You need to have the forecasts one way or another, and you need to get the revenue estimates. So these are small and capital R. And the objective, just exactly as what we had, total expected revenue. Allocate seats to classes to maximize the total expected revenues. Same thing. Yeah, so this partition versus serial, maybe I was already trying to draw this picture. So if you have several classes, you can say, well, I want to decide for these, and for these, for all my 4 classes. So that would be partitioned. So the serial the nesting booking is that we look at the highest paying class versus everybody else, and we are deciding the X for them. And then we look at the remaining classes and deciding the seat reservation again for the highest paying, and the rest is for the others, and so on. So we always look only at 2 classes, highest paying and the rest. And yeah, I don't think we need to go into examples of what they do with the specific classes that they consider here. Right, so this is basically nested buckets. Protector for class 1 from all the other classes and so on. Yeah, should have drawn my picture. So deterministic is not particularly interesting. If we know how many business passengers we have, then we protect seats for them and the rest for the second highest paying class, and if there is something remains for the third, and so on. Yes, the more interesting is this models with the expected revenue, and this EMSR is expected marginal seat revenue, and don't worry about what this A and B models, what they stand for. So yeah, they have a different model, but the same problem. So the demand for each class is separate, and again, that's also our assumption that the demand is independent, that we don't divert business passengers to the more cheap leisure seats. We're saying that, well, leisure are leisure, business are business, and they don't influence each other. The demand for each class is stochastic and represent for probability distribution. That's exactly as we had, except that just for simplification, we said that the leisure demand is actually deterministic, but that's because I was trying to use the simplest model, which still makes sense. Yes, this issue that the lowest class books first, and then the next, and then the business. And the booking limit, yeah, determined once. I mean, you can do the recomputation every day or every minute or as often as you want, but at least within a single model, the single instance of the problem, we're doing it only once. So that's exactly what we did. Yes, and what we need to calculate the optimal protection levels, well, we need this probability. So this is kind of the complement distribution function, the probability that the number of certain type of passengers will be larger than, you know, the SI or whatever, than the certain number. Right. So this is essentially the same as our distribution function, but well, they look at 1 minus that in the complement distribution function. So this is what you need to do. And here it's, well, I'm not going to go into details of that, but turns out that this is essentially the result that they get is exactly the same as we have. So if you look at this formula, they want to find this pi1, the optimal protection level for class 1. And what they say is that the probability distribution function, while they use the complement distribution function of this pi1 should be equal. If you divide both sides by R1, then essentially what you get is that the probability should be equal to the ratio of R2 and R1. And this is exactly what we have. So our formula was that the distribution function of the optimal seat reservation level should be 1 minus the ratio of the prices of the revenues. And this is exactly what they have. But they don't tell you how to arrive at this formula. So in some sense, they learn less than we do. They have the fish, and I'm giving you the fishing rod. You don't need the fancy ePods or any other system to do this EMSR, B, or whatever calculations. You can do these calculations by yourself. Determine the expected revenue. Build the full graph of how the expected revenue depends on the number of seats reserved for the business passengers. And then, well, you can look at the graph and determine the maximum, or you can go through differentiation if needed. It's not going to be needed on the homework, but in principle, you should have enough knowledge for that. Anyway, so yeah, that's the kind of final formula that, or the most important formula that they get, and it's exactly as we do. Then they also have, yeah, some examples with few classes. They also do the variance of the forecasts. We don't do that, and so on. So yeah, that's the end of the lectures. So yeah, you may use the MIT lectures or anything else, and well, hopefully you know what's different and what's similar between them and us.